How recurrence relations model finance. The world of finance is interconnected. In this video, I'll explain how recurrence relations relate to various financial concepts. Some common terms and notation to understand in this video. V0 is the principal, which is the amount borrowed or invested. Vn is the value at the end of the period. R is the common multiple and is closely related to the interest rate. N is the number of periods, and I is the interest. Example 1. $500 is invested and earns 6% per annum. 6% of $500 is $30, so the investment increases by $30 each year. Example 1 as a recurrence relation. V0 is equal to 500 because $500 is what was invested at the beginning, the principal. The next number in the sequence is equal to the previous number plus 30. It's plus 30 because that's the amount of interest each year. So after the first year is 530, 560 after the second, and so on. There are different ways of approaching example 1 as a formula. One way is what I've done here, which is Vn, the total, is equal to V0, the principal, plus the annual interest times N. So for our example, the principal was $500 and the annual interest was $30 a year times N. So if I wanted to work out the value of the investment after 4 years, it'd be 500 plus $30 a year for 4 years. If I was to graph this over 4 years, you could see that this is a straight line because it's going up by the same amount each year. So let's recap simple interest. The interest is equal for each time period. The simple interest always creates a straight line graph, but its real-world applications are minimal. A $400 item depreciates by 15% flat rate. So 15% of $400 is $60, so the item decreases by $60 each year. So as a recurrence relation, V0 is equal to 400 because that was the value of the item at the beginning. Vn plus 1, the next number in the sequence, is equal to the previous number minus 60. We're taking 60 each time because that's how much value it's losing each year. So after the first year is $340, after the second $280, and so on. Flat rate depreciation is very similar to simple interest, but rather than adding, we're going to be subtracting. So for our particular example, the principal was $400. The annual depreciation was $60, which we're going to take each year. So after 4 years, $400 minus the annual depreciation of 60 times 4 years gives us $160. Our simple interest graph was a straight line going up. Flat rate depreciation is a straight line going down because it's losing the same amount of money each year. So let's recap flat rate depreciation. The depreciation is equal for each time period. Flat rate depreciation always creates a straight line graph. It is just like simple interest, but effectively it's negative interest. That's why a simple interest graph goes up and a flat rate depreciation graph goes down. But just like simple interest, it has limited applications in the real world. $500 is invested and earns 6% per annum compounding annually. One way of approaching this is 6% of $500 is 30, and then we take the 500, add 30 to it, we get 530, work out 6% of that, which gives us $31.80, and then add the $31.80 to the 530, which gives us $561.80. If you're thinking that there's a better way to approach this, you are correct. A better approach is this, but we need to do some background first. To increase by 6%, we take 100%, we add 6%, which gives us 106%. 106% is the same as 106 over 100, which is equal to 1.06. So to increase by 6% each time, we multiply by 1.06. This multiple is called capital R in most textbooks. Let's approach example 3 as a recurrence relation. V0 is equal to 500 because that was the principal. To get the next number in the sequence, we're going to keep multiplying by 1.06. So 500 times 1.06 gives us 530. Multiply that by 1.06, we get $561.80, and we keep multiplying it. Let's look at example 3 in more detail. To get V1, we're multiplying by 1.06, or 1.06 to the power of 1, gives us 530. When we get to V2, one way of approaching it is going 500 times 1.06, doing that twice, or 500 times 1.06 to the power of 2. V3 is the same as multiplying 500 by 1.06 3 times, which is the same as 500 times 1.06 to the power of 3. V4 is the same as multiplying by 1.06 4 times, or 500 times 1.06 to the power of 4. To find Vn, what we were doing before was we were taking the principal and we kept multiplying by r each time. In other words, we can simplify to this formula that Vn is equal to V0 r to the power of n. So for our particular example, V0 was equal to 500 because that was the principal. R, the common multiple that we were using, was 1.06. So if I wanted to work out V4, it'd be 500 times 1.06 to the power of 4, which gives us $631.24. This graph for compound interest looks like a straight line, but it's actually curving up. If we extend the graph over a longer time period, we can see the more classic upward curve. So we just got to be careful when we are doing a compound interest graph over a short period of time. So let's recap compound interest. The amount of interest increases each time at an accelerating rate. The more money that you have, the faster it grows. Compound interest creates an exponential graph, but it may not always look like that at the beginning. Compound interest is a fundamental component of most real-world financial problems. A $400 item depreciates by 15%, reducing balance. One approach would be to work out 15% of $400 gives us $60, and then take that $60 away to give us $340. 15% of $340 gives us $51, and then take that away. However, there's a better approach. To decrease by 15%, what we do is we take 15% from 100%. That gives us 85%, and 85 over 100 is equal to 0.85. To decrease by 15%, we multiply by 0.85 each time. This multiple is called R in most textbooks, just like it was for compound interest. Example 4 as a recurrence relation is very similar to compound interest. V0, the principal, is equal to 400. To get the next number in the sequence, we multiply the previous number by 0.85. 400 times 0.85 gives us 340. Multiply that by 0.85, we get 289, and so on. In more detail, V0 is equal to 400, V1 is equal to 400 times 0.85, or 400 times 0.85 to the power of 1, because it's 1 year, gives us $340. To get V2, it's 400 times 0.85 twice, which is the same as 400 times 0.85 to the power of 2, which gives us 289. V3 is the same as 400 times 0.85 3 times, which is the same as 400 times 0.85 to the power of 3. V4 is the same as 0.85 multiplied 4 times, which is the same as 400 times 0.85 to the power of 4. This leads nicely onto the formula. Vn is equal to V0 times as many R's as you need, and it simplifies to this formula, which is the same formula as what we use for compound interest. For our particular example, V0 is 400 and R is equal to 0.85. If we wanted to work out the value after 4 years, we could go 400 times 0.85 to the power of 4, which gives us $208.80. Reducing balance depreciation over a short period of time can look like a straight line. However, over a longer period of time, you can see the more classic curve. It depreciates a lot at the beginning and then starts to flatten out as it loses its value. Let's recap reducing balance depreciation. The amount of depreciation decreases each time period at a decelerating rate. It creates an exponential graph that curves up so that the graph never hits zero. Reducing balance depreciation is effectively compound interest but with negative interest rates, and this is why the formula is the same for both compound interest and reducing balance depreciation. So to review, recurrence relations that use addition, subtraction, multiplication can be used to complete problems relating to simple interest, flat rate depreciation, compound interest, and reducing balance depreciation. Thanks for watching. Please subscribe and hit the like button. Please leave a review and a comment. I'm not a financial advisor. I'm an experienced mathematics teacher with a passion for teaching financial literacy. Please read the disclaimer.